Our lecture today is on isolobal analogy. Isolobal analogy is a topic that you might have encountered with CD212 if you have taken the inorganic chemistry course in integrated PhD. So I'm afraid it will be a bit of a repetition for those who are coming from integrated PhD stream. For those who are coming from the undergraduate stream or from or those who have not taken CD212, I hope it will be a refresher course on some of the topics that you might have heard about in your inorganic chemistry course. First, let me start by wishing you all a happy new year. I hope we have a better year than what we had in 2020 because of all the virus issues. So I also want to tell you that we only have about 6 more lectures in this course, and so I would have to speed up a little bit. I hope you will be able to do some extra reading in order to catch up. I have also posted the answers to the test that was given. It was a lengthy test. I know that. These tests have to be speeded, as they call it, because we have an open book exam. So let me have this first slide gives you a link to, this is a link. Let me just see if my pen is functional. Yes, this is a link to the Angewandte-Chemie paper that Hoffmann wrote after the Nobel lecture was given. You could hear the Nobel lecture in the Nobel website as well. So this is the background. I will just briefly tell you what we have in store. Organic structures are extremely well systematized in the sense that people know how to modify organic structures in order to derive new structures without violating any basic principles of chemistry and arriving at a new structure which might have a stable existence. So if you want to do such transformations in other parts of chemistry, like inorganic chemistry and organometallic chemistry, how do you do that? That's the real question. So what do I mean by this? For example, here we have a CH2 group. The CH2 group has been replaced by an oxygen and it forms a perfectly stable structure. Similarly, there are 2 hydrogens which are here in this position. They've been replaced by other alkyl groups or aryl groups. And 2 hydrogens can be replaced by an oxygen if you replace both of them simultaneously with 1 oxygen. So these are replacements that produce fragments which are stable. And so one might say that it is possible to arrive at new structures without any difficulty. So in transition metal chemistry and in organometallic chemistry, this is something that was not available for a long time, and it was Hoffmann who made this observation that you have some fragments in organometallic chemistry which are repeated. For example, in the ferrocinyl structure, you have the same cyclopentadienyl metal fragment repeated. So this green fragment is repeated here, right? I should have drawn it up to here, right? So this and the green fragment are the same. Similarly, the MCO2 fragment is repeated in other places as well. MCO3 fragment is repeated in other places. So these are fragments which, if we understand, we should be able to derive a similar framework for organometallic chemistry, just as we have done in organic chemistry. So this is roughly the basis for doing this, and we have already encountered quite a bit. So this might be considered almost like a summary class for what we have been talking about in the first half of the course. So Roald Hoffmann called Woodward the supreme patterner of chaos. And in fact, Hoffmann himself is the supreme patterner of organometallic fragments. CH4 is a saturated organic fragment from which we derive many other smaller fragments in organic chemistry. So what is an equivalent organometallic fragment which we can use, which we can utilize as a basic building block from which we can build more complex organometallic chemistry fragments? If we look at the saturated organic fragment, it is methane. You have a total of 8 valence electrons. So the corresponding organometallic fragment which has got 18 valence electrons, and it has the most commonly occurring structure, which is the octahedral fragment, is CrCO6. So we will use that as our basic starting point for discussion of organometallic fragments. If I take CrCO6, I can pull out each carbon monoxide one by one. So for example, I can utilize this fragment, and I can remove this carbon monoxide, for example, and derive this second fragment which has got only 5 ligands. So from this fragment, I have derived the MCO5. By pulling out 2 carbon monoxide units in the axial, in the equatorial framework, then I derive a different fragment, which is ML4. Now, what Hoffmann went on to say was that these organometallic fragments have got fundamental relationships to the organic world. So let's start with the evolution of metal orbitals, something which we have seen earlier. I would repeat that. When you form a 6 coordinated complex with a metal and 6 ligands which are coming towards the metal, then what we do is we pre-order the orbitals which are available on the metal. We reorient them so that we have 6 available orbitals for interacting with this ligand. So we are very familiar with this. What we mentioned was, we have already done this, we said that we will combine, we know this from simple transition metal chemistry also. The valence bond theory has taught us that if you make a hybrid set of orbitals from 3 p orbitals, 1 s and 2 d orbitals, we will get a set of octahedral orbitals. So the energy level of these hybrid orbitals would be somewhere in, it will be a weighted average of these orbitals, and so it would be somewhere here. We will have 6 orbitals which are the result of 6 equivalent orbitals, which are the result of mixing sp3 and d2. So let's take a look at these mixed orbitals. How do they look like? They will look like as if they are pointed towards the plus x plus y minus y plus z minus z axis. That is for our convenience, that if we orient the ligands like that, we will have very nice combinations. We don't have to rehybridize them again. So this are the set of valence orbitals that we would derive from the 3 p orbitals, 1 s orbital and the 2 d orbital. Okay, so the energy level was somewhere here, and notice that we have left out the dxz, dyz, and the dxy orbitals. Why did we do that? Because these are not oriented along the axis where the ligands are coming in. So these became non-bonding orbitals. You already know this non-bonding set as the T2G set of orbitals, where you can house the metal electrons in a very safe fashion. So what we have done is that we have set of 6 orbitals which are available for interacting with the ligand, and 3 orbitals which are left behind on the metal at the same energy as the d orbitals. So these are non-bonding orbitals and these are available for bonding. And if we mix the two, the 6 ligand orbitals which are coming in, which are usually the lone pairs. In carbon monoxide, we said that that's the 3 sigma or the 5 sigma, as whichever way you count. And if you look at ammonia, it will be the lone pair that is coming in. So you can form, for example, with chromium hexacarbonyl or hexaamine chromium, you can form a nice complex, apparently. So these are the incoming ligands, which have 6 into 2, 12 electrons, 6 pairs of electrons. These are stabilized by interacting with what was available as the hybrid octahedral set of orbitals, empty orbitals, and the non-bonding set of orbitals that are there. So if we proceed further, what we realize is that we can now fill up if you choose the metal as chromium, then we end up with 6 electrons on the chromium, and so these orbitals are also filled, and correspondingly we will fill up the non-bonding T2G set of orbitals. These are the bonding orbitals. And these are anti-bonding orbitals. In a sense, we have combined everything in a valence bond fashion to form hybrid orbitals. Because there are individual orbitals, the energy levels that you might derive from a computational standpoint might be slightly different. The levels might be split, but approximately, so I would call this the 3M model, Mickey Mouse molecular orbital model. Okay, so this is really a very simplified version of the molecular orbital picture, but it is extremely useful because it tells you immediately the origin of the 18 electron rule. If you have this, the maximum number of electrons that a metal complex can have is 18 if you have this octahedral framework. So let's now talk about the fragments that would be formed. Suppose I have an ML5 fragment. What would happen to these energy levels? What would happen to the orbitals? So here, what we need to do is to go back to the hybrid orbitals that we considered. We prepared 6 empty hybrid orbitals on the octahedral fragment, and one of them will not be able to interact with the ligands because only 5 ligands are coming in. The ligand that was coming in along the plus Z axis is now absent. As a result, you would end up with one orbital which was hybridized, suitable for accepting the ligand, is now vacant. And that orbital would have this shape. So that orbital would have this shape and it would be empty, right? It would not have a pair of electrons to interact with from the ligand, which has not come in, right? And the T2G set, on the other hand, remains unaffected. So we now have a fragment which has got an empty orbital and which has got a set of 5 ligands. Now, Hoffmann figured out that if I think of the organic fragment, methyl fragment, the methyl fragment with 1 electron in its empty orbital is very similar to an ML5 5 unit, where one ligand has been removed from the ML6, which is the saturated fragment. So here what we have done is we have taken CH4 and we have removed one ligand, that is the hydrogen which is coming in. So we have one electron there. So how can we make this ML5 unit look like this CH3 radical? What we had was chromium, where we filled up exactly the 6 electrons. Now, if I want to put one electron on this orbital which is empty, then I need to move to the right side of the periodic table. So from chromium, I move to the right, I come to manganese. And if I have manganese, I have a D5S2 configuration for the metal, and that would be, in fact, D7 configuration for a metal which is interacting with ligands. So I would fill up 6 electrons here. Let me remove this confusing chromium. 6 electrons here, and 1 electron would go into the higher lying orbital. So this MnCO5 fragment, which has got 1 electron, is exactly suitable for interacting with another species which would come in with a 1 electron species. So what is a methyl group like? So let me emphasize the fact that these are not isostructural fragments, because this has got 5 ligands and this has got 3 ligands. So these are not isostructural. These are not isoelectronic either. This has got a whole bunch of more electrons than what the methyl group has. Instead, the frontier orbital that is present on the manganese and the frontier orbital present on the methyl group are similar. So it's only a comparison of the frontier orbitals that we are talking about. So if you do an extended Huckel calculation, you will notice that the MnL5 fragment, Hoffmann actually used hydrogen as a ligand instead of carbon monoxide. I have computed for you the carbon monoxide structure MnCO5. I will show it to you in a minute. But this is the picture that you have with 1 electron which is sitting on a vacant orbital pointed away from the ligands on the metal atom. Same thing is happening here for the methyl. 1 electron is housed in an orbital which is pointed away from the ligands, and it is available for interaction with an incoming fragment. So we can actually ask the question, what will a methyl radical do? A methyl radical is in fact something that would combine with another methyl radical and form ethane. Now we ask the question, what does MnCO5 does? What does it do? It combines with another MnCO5 and it can result in 2 MnCO5 units forming a metal-metal bond. Okay, this should not make it look as if it's a double bond, so I will remove that. So here you have an MnCO5 single bond that is formed. That's the Mn2CO10 structure that you're all familiar with. You can also combine the MnCO5 fragment with another methyl fragment, and that's MeMnCO5, another common molecule that you have already encountered in your organometallic chemistry course. So the complex that is formed between MnCO5 and methyl, or the dimerization of MnCO5, are reactions which are typical of a radical species like a methyl radical, and so it is not surprising at all. Let me see. Let me go ahead and I will show you the orbital pictures of MnCO5 as well in a minute. Now we would like to proceed with removing 2 ligands. Now let's proceed with removal of 2 ligands from the octahedral fragment that we started out with. What I have for you on the top is the octahedral fragment. This is ML6. The 6 orbitals that are prepared. First we removed one ligand, and then now we are going to remove this ligand also. We remove this also, and then we will end up with a fragment which will look like this, which means that I have ML4, okay, where I have removed two equatorial ligands from the octahedron. What will I end up with? It's easy to see. You will end up with two orbitals. If I just convert this picture, I'll have two orbitals which do not have interacting fragments, or which will not have interacting ligands to form the nice bonding orbital combination. So these two orbitals are now going to have a slightly higher energy than the three T2G orbitals that we left behind from the d orbitals. So these are pure d-like orbitals. These are hybridized orbitals. So these are hybrid orbitals. So these hybrid orbitals, notice there are two of them, are in fact degenerate when you look at the valence bond picture. They are degenerate in energy. Now, unfortunately, this hybrid orbitals can also combine to form a symmetric combination, and that would be this, and an asymmetric combination, that is just like you did the initial combination of A plus B plus C, etc. You can combine these two orbitals now, deconvolute them to produce two new orbitals which will be symmetric and asymmetric. Okay, now this is not unusual in chemistry. Let me look at the water lone pairs. If you remember, water has got two lone pairs. These two lone pairs are what we call as rabbit ear lone pairs. These are present in our high school textbooks and later also, and these readily explain the very nice structure of ice, the hydrogen bonding that is formed, etc. But if you take an isolated water molecule and do spectroscopy on it, you find that the energy levels of these two lone pairs are different. They are two different lone pairs which are present. One is a symmetric combination and the other is an asymmetric combination. So we call this the sigma lone pair and the pi lone pair on water. So there are two lone pairs on water, two different types of lone pairs on water, and the moment water wants to interact with another molecule of water in the ice structure, for example, it will combine these two in order to generate these rabbit ear lone pairs. So it is convenient to talk about these rabbit ear lone pairs, but in the isolated water molecule, they in fact have got a different form. They have a sigma form and a pi form. Okay. Now, this is the fact that they have the analogy to water comes up because I initially started with two equivalent lone pairs, and I showed you that spectroscopically it is possible to see that there are two different energy levels and two different forms. Now the same thing happens here. We have a degenerate pair. We can combine this into a symmetric and an asymmetric combination of two orbitals. It turns out, one more thing that I would like to say is that if we have these two orbitals are fairly close in energy. And so if you put two electrons here, they end up one in each one of these orbitals. So it forms a triplet state as the ground state. Similar thing happens in CH2. If you take CH2, the ground state is in fact a triplet. Okay, and that is because these two orbitals are so close in energy. There also you have a sigma and a pi set of orbitals, and these orbitals are occupied with 1 electron each. Excuse me for a minute. I have a class. So I have 1 electron in each one of them. So let me go back to the periodic table, and if I want to have 2 electrons in these 2 combinations of orbitals, I have to have a total of 8 electrons. So for example, with chromium, we just filled up this and said that it's a saturated system. When we wanted 1 electron only, we just went from chromium to manganese. Now we are going from chromium all the way to iron because we want 1 more electron to fill up these orbitals, 1 electron each, in order to make a fragment which will look like the CH2 fragment, which is also a triplet species. There is a slight difference between the 2 forms, the energy levels of the 2 forms. This is from an extended Huckel calculation. Hoffmann showed that the symmetric form is in fact the higher lying level and the asymmetric form is a lower lying level. The reverse is true for the CH2 groups. Okay. So that comes from the hybridization of the S and the P. P lies higher in energy. So the more noded one, if I might call it that, is lying higher in energy. So in the case of the metal orbitals, the S is lying higher above the D, and so the less noded one is higher in energy compared to the D. Okay. Let's now proceed to what would happen if I have a CH2 group. A CH2 would combine with another CH2 to form ethylene. So here we have on the left side of the screen formation of ethylene from 2 carbenes. If I combine 2 FeCO4 fragments, they do combine. 2 FeCO4 fragments do combine and they form Fe2CO8. Unfortunately, this fragment is unsaturated. So is this fragment. This is also unsaturated. This is also unsaturated. This is also unsaturated. So this fragment reacts with several species, like it can react with the carbene, it can react with an oxygen, so on and so forth. This fragment is more reactive. So when you talk about isolobal relationships, when you talk about similarities in these fragments, they do not transfer completely to reactivity. They transfer very often to structures. So Fe2CO8 reacts with carbon monoxide to form Fe2CO9 and form a saturated structure. Ethylene can also react with a carbon monoxide and form a cyclopropanone. That's not an impossibility, right? So that's also a stable molecule. Fe2CO9 is also a stable molecule. Now, FeCO4 can also interact with CH2, and that turns out to be a lot more stable. That is a carbene. We have already encountered that in our lectures. So FeCO4 can react with the carbene. This is also a stable molecule that can be generated. But what is interesting and what Hoffmann did was the explanation of very complex structures using this analogy that he derived. He said that FeCO4 is equivalent to CH2. And he used the symbol. He used the symbol where there was a lobe in the lower half of the equation. So it is a double-headed arrow in which there is a lobe which is hanging on it. He said that that is the symbol for an isolobal relationship. So that's a CH2. Okay, so if you take cyclopropane, this is cyclopropane. You can now replace one CH2 group with an FeCO4 unit, and you get the familiar molecule where FeCO4 is interacting with an olefin. Only thing is now you're drawing it in a different form. You're drawing it in the form of a metallocyclopropane. I have already mentioned this to you that when you have very electron withdrawing substituents, the structure in fact becomes exactly similar to a metallocyclopropane. So if I now replace two of the CH2 groups with FeCO4, I come to another very common molecule, which is a methylene fragment, which is interacting with a Fe2CO8. Fe2CO8 has got a double bond between the two iron atoms. It can become a saturated species by interacting with the CH2 group. And that's what we have done here. We can replace the third CH2 group with another FeCO4, and that gives us a trinuclear structure. This time I have replaced the iron with osmium, and the very simple reason is that the iron structure is also there, but it has got two bridges. So in order to avoid the complication of understanding the nature of the bridge, we have moved to osmium, triosmium dodecacarbonyl species. Okay. One more complication. You can remove one of these iron atoms and replace them with a tin by saying that it is as like a CH2 on this side and a CH2 on the other side. So you just are left with the carbon. So this turns out to be a spiro metallocyclo pentane, I guess. So this is a spiro compound, which is very readily explained using this isolobal analogy. Moving forward, let's make now an ML3 fragment. If I make an ML3 fragment, I would have to remove, I can do it in two ways, but in order to derive a fragment which very commonly occurs, which is MLLL, you need to remove one phase. So let us remove three ligands that are coming in on one face of the octahedron. So I'm removing one face of the octahedron, and that gives me a fragment which is very common. If I do it on an octahedron, I can do it on the plus x plus y and the minus z axis. And that's what I drew in the previous slide. I removed it from plus x plus, actually in this diagram it is different, but it's plus x plus y and minus z in the next picture that I have. So I should turn it around in a slightly different fashion. So I turn it around in order to see it like a fragment which we normally encounter. I have drawn it upside down here, but it doesn't matter. What I have is three orbitals which are pointed in the three directions which are away from the MCO3 unit that I have. So what will the count be, electron count be, and what will be the nature of the orbitals? If you remember, the hybrid orbitals are going to be just pointed in the plus x plus y and the minus z axis. Those are the three orbitals. And if I want the right number of electrons to be occupied on these three, so if I want to compare it with the CH fragment, remember the if you remove 3 ligands from a methane minus 3H from CH4, I will end up with 3 orbitals on the carbon also. So if I want to make an equivalent statement, if I want to make a comparison, then I need to move one more step in the periodic table. So we went from chromium, we went to manganese, manganese to iron. Now we're going one more step, that's cobalt. So COCO3 will have a D9 occupancy. So if you have D9, then 6 orbitals can be accommodated in the T2G set. 6 orbitals are here, T2G set, and 3 electrons will be on these 3 orbitals. Now, the same thing that we did with water happens here, with CH2 happens here. We add and subtract these 3 hybrids to generate a totally symmetric combination and 2 degenerate set of orbitals which will be asymmetric, and the analogous CH fragment is also split like that. It also has, and as I told you earlier, the lower noded one is the lowest energy one in the carbon, whereas for the cobalt case, the A orbital turns out to be higher lying in energy. Okay, now this being the case, let's try and see if we can interact these two fragments together and make any sense out of the structures that we get. So what we have written now is an isolobal analogy between Cr or CH and D9ML3. And what we are going to get right now is an analogy between some complex clusters which are available in organometallic chemistry, and using the isolobal analogy we can see the relationship to organic chemistry. So here I have for you on the leftmost side of the top line tetrahedrine. Tetrahedrine is just 4 CH units. 4 CH units combined together. In a tetrahedral arrangement, you get tetrahedrine, which is a saturated molecule. If I take a cyclopropenyl system and interact it with COCO3, I have replaced one of the CR groups. I do an isolobal replacement with COCO3. I get a corresponding fragment, which is another stable molecule, which I don't think we discussed this molecule, but it is a cyclopropenyl ligand, and it forms a very stable complex with the COCO3 unit. If I replace 2 of the CR units, I can do that here, replacing one more. So I have replaced 2 of the units. Just to be consistent, I'm going to draw that in red. So I have replaced one CH with COCO3 and another CH with another CH also with COCO3. That's another isolobal replacement, and we get this molecule. What is this molecule? This molecule is nothing but an acetylene coordinated to two COCO3 units. So you can see that there is a very simple relationship between the fairly complex molecule that we have in front of us. That's the CO2, CO6 coordinated to acetylene and tetrahedrine. So these two are very simply related to each other. Of course, you can do one more replacement of a CH group. You can do one more replacement of a CH group, and that's what has been done in this. You replaced one more, and you end up with a carbene, which is triply bridging 3 CO3 units. This is a carbene, and the carbene is coordinated to 3 CO3 units. Okay. Of course, you can replace everything with a metal and you get the IR CO12, IR4 CO12 unit, which is also a stable molecule. So you can see that a very simple analogy which Hoffmann used between the ML6 and CH4, ML6 and CH4 was useful for deriving 3 different fragments which are very common in organometallic chemistry: the alkyl radical, the methylene fragment, and the methine unit. So all of them have got analogous structures in organometallic chemistry. Now you can go ahead and build, wherever there is a CH unit, you can replace it with a D9ML3, and we can hope to form a stable structure as long as steric effects are satisfied. As long as sterics is not a problem, we can do this. One more thing that we need to remember is the fact that we are looking at 18 electron structures. I have already told you that 18 electron structures are not necessarily needed. We can have 16 electron structures also. So we can have some complications from 16 electron fragments. But first thing I want to do is to give you a simple difference in the way in which we remove the ligands. We removed, for example, in the case of, let me tell you what would happen if we removed a trans ligand. We removed a cis ligand in order to generate an ML4 fragment. Okay. Suppose in the ML3 fragment, let's remove 2 trans ligands. Okay, we'll take the ML3 ligand and try to get the ML3 in a meridional fashion. So what would happen to this system? So 3 orbitals. So I'm jumping a few steps because we're running out of time. We have 3 orbitals which are left behind in an ML3 system, and in addition to it, what we have done is, because we have removed 2 trans ligands, what we have done is the dz squared, which will not have a partner to interact with, and so the dz squared will also be in the non-bonding set. Similarly, the pz, because we have removed trans ligands along the z-axis, we have to remove this, but we have already mixed it, so we have it in the we have 3 of the mixed variety, and we have 1 which is non-bonding. Let me just go to a specific example. Let's start with this system ML3, in which we are going to derive the fragment orbitals. So we have 3 T2G orbitals, and that is already mentioned here. Let's go to this figure because it's easier. So this 3 orbitals are coming from the T2G set here. Because we removed the Z ligands from this ML5 fragment, the dz squared orbital, which was in the mixed state, we had these 6 orbitals here, remember? The dz squared is going to come back to the non-bonding state. Non-bonding, it's not going to interact with anything much. And we also have the pz. So the pz is also going to be non-bonding. So what we end up with in a D10ML2 system, D10ML2 system is a very similar fragment that you have to a CH2 fragment. Only thing is, now we have put 2 more electrons into the non-bonding orbitals of the metal. So we have a filled set here and 2 electrons which are 1 in each one of them in order to derive the analogy with CH2. So this is basically an MCO2 fragment, and the M can equal nickel. Okay, so if we remove trans ligands, then the dz squared orbital comes back all the way down to the non-bonding set, and this is something that happens when you have late transition metals like ML2 systems, and then they also can behave like a CH2 fragment. So let me now show you some of the orbitals I have for you here. It's yeah. Yeah, so let's start with the MnCO5. This is the MnCO5. What I have done is a calculation on MnCO5 plus. The reason is odd electrons can make computations very difficult. So I have removed that electron, but MnCO5 neutral will have 1 electron sitting in this nice orbital, which was pointed towards the incoming fragment. The ML5 is pointed in the opposite direction. So here is another ligand which is coming in. It will see a nice totally symmetric combination which is able to accept a pair of electrons. So you can fill this with H minus, you can fill this with another carbon monoxide lone pair, you can fill it with anything else that you want. Similarly, I also have this is FeCO4. This is FeCO4. Remember, FeCO4 is a CH2 fragment. So again, I have made it a singlet to reduce the computational difficulties involved. So here is the empty lobe, and here is the filled set of orbitals. In real life, these 2 orbitals are filled with 1 electron each. Okay, so that's the CH2 group. Again, you find the totally symmetric combination and the unsymmetric combination, which is, in this case, it is filled. But as I told you, these 2 orbitals are filled with 1 electrons each in the CH2 system. Even in organic fragments, you will end up with singlets and triplets. CF2, for example, is a singlet. CH2 is a triplet. So small changes in the molecular fragment can change the electronic states when you have 2 closely lying orbitals. And that is what we are encountering here. To just simplify the calculation I have made for you, FeCO4 in the neutral singlet state, but remember in real life it is a triplet. I can do the triplet calculation and show you that in fact that is a lower energy form. So it will react as if it is a CH2 group. So this is the form which we normally write it. So you can visualize it in that framework that I showed you. Now I will show you the last one, which is MCO3. MCO3, I have not done it perfectly. What you have on the left hand side, you see that there is one highest high lying orbital which is empty in this case. Green and yellow orbitals are empty orbitals according to this representation, and the two orbitals are filled. So what I have done is I have filled them. In real life, this will be this will all be partially filled with one electron each, and the metal will be cobalt. In order to simplify the calculation, I have made it an NiCO3 fragment so that it will be an even electron species. But these are the three frontier orbitals which we are talking about. Okay, so there are two lobes here, and there are two lobes here, which you can see here, two lobes, and then a symmetric combination, which you can see here. So these fragments, I have not fully completed the table that I showed you in an earlier time. I had shown you this table of orbitals, but here is the, let me stop here. I will entertain questions. This is the paper which is available in IPC website also. Professor Jemis has put it up in his website. So in fact, if you search for it, you get this as the first hit. So you can see that. Now, can we have any questions that you might want to ask? Okay. So if there are no questions, let me tell you that the answers have been posted in the website. I would like you to go through the answers. I have not exhaustively written everything. I have given a key. You can have variations of this key, especially in the structure. In the question on fluxional molecules, for example, I have written very briefly, but any one answer in that would do, because it's not an exhaustive listing of all the fluxional forms that I'm asking for. So I hope all of you are familiar with the Teams website, where you can find the files. It's under files. So you should be able to locate it. Any other question? Any question? No questions are there. Okay. So I will stop here for today. You can log off. So the next 6 lectures will be completely on reactions, and we will talk about reactivity and catalysis.